Morning, everyone. Welcome to the March CBEC meeting. We'll get rolling here in a moment as folks get logged in. Start with a few announcements. The CBEC is, of course, a nonprofit organization dedicated to the pursuit of excellence in design, construction, and other aspects of building enclosure. So we're here to try and spread knowledge of building science among architects, consultants, contractors, and building owners. We accomplished that through our very robust board, including Amelia Davis as the Secretary for Northwest Partners, Jeff Didion from OAC is our treasurer, Amanda Prott from Morrison Hirschfield is our education chair, Clifford Marvin with RIB is our membership chair, Hillary Roy does our venue coordinations, which hopefully we'll get back to in the fall. Bill Thordarson with Bain Associates is both our student outreach coordinator and our sponsorship coordinator. We're looking to fill some additional board roles with Joel moving to Texas. Grace Wong from OAC is our communications chair. Jeremy DeWitt manages our website. Penny Short is our board administrator. Phil Martinson from Spokane is our representative from that area. And then Rob Bechtel is our past president. If you have ideas for future presentations, please reach out to Amanda or myself. And if you're interested in sponsoring a future meeting, please reach out to Bill or myself. Our next meeting will be April 21st. It's an evening meeting. And the presentation will be Brutal Honesty, an Architectural Exposed Concrete in the Pacific Northwest, presented by Brad Carmichael from 4EA. So we are looking forward to that. And a couple other regional events. IBEX International Convention and Trade Show is going on right now in Orlando, Florida. CSI has their annual ProSpec dinner and trade show on March 22nd. That looks to be a great event. And then their April meeting is on the 14th, and it's titled April Showers Bring Mayflowers, or How to Lick the Building Envelope. So kudos to whoever is crafting their presentation titles. Today we have Roy Denoon from CPP, and the topic is wind engineering for building envelopes. What are the options? Roy is a principal with CPP and has some great experience with wind tunnel testing and standard development for wind design in buildings. Roy, if you're ready to take it over.
Yeah, thanks, Nathan. Yeah, screen share going.
I should mention that we'd like to use the Q&A throughout the presentation. So if you have questions for Roy, please enter them into the Q&A and we'll address them kind of as we move throughout.
Sounds good. Yeah, thanks, Nathan. And just in one of these wonderful bits of planning, it's St. Patrick's Day, so you're given a Scotsman to talk to you. Make of that what you will. So today, I just want to give a bit of a talk about how you do wind engineering for building envelopes. What are your options? Where are the limitations, a little bit of the code? Where do you use the wind tunnel? What's best where? And also have a look at some of the limitations of the code and also some of the changes that are coming up in the SC 722 that was just published. There we go. So this presentation is being submitted right now for AIA accreditation. So hopefully we'll get that through in the next couple of weeks, but these are the wonderful AIA learning objectives, which you can happily ignore while we talk through the rest of it. So you're probably all aware of the codes. I mean, there's just a collection of them from 705 to 710 to 716, the ASCE SEI loading standard. And what you'll have noticed is that every time they republish one, it keeps getting bigger. But does it have all the answers? No, it really doesn't. There are limitations, and the code itself does recognize the limitations. This is just to remind you that the new 722 has just come out. I don't have a physical copy of it in hand yet. So I don't know quite how thick that is compared with the others, but we have taken some stuff out, but we've put a heck of a lot of other stuff in. So it's probably gonna be a little bit thicker again. So the code does kind of limit you in what you can use it for, the standards. So, and it says you can use the standard to get the wind loads, the local building envelope pressures, if it complies with the following conditions. The structure is a regular shaped structure. Well, that's open to a bit of interpretation, and I don't know many architects who like to consider their work as particularly irregular shaped. Then the second one, that applicable to building envelopes, which says doesn't have a site location where you're going to see channeling effects or buffeting in the wake of upwind destructions, warranting special consideration. So that's really saying you've got a building that's surrounded by other buildings, usually of a similar size, and that's causing an accelerated wind flow or additional turbulence coming onto your building. And there's just the definition of regular shape, having no geometrical irregularity in spatial form. Where does that start and finish? Just a box? Yeah, arguable. So we'll look at some examples of things that you can consider regular shaped, and a few others that definitely fall out of that category. So let's just look at some of the basics first, though. Here we've got, this is just a time history of wind, showing wind speed in some non-dimensional unit. Let's just call it miles per hour up the left, and then time in minutes along the x-axis there. And what you'll see is we get three components to the velocity. We've got the longitudinal velocity, so that's the speed in the direction of the wind. And then we have a lateral and a vertical component. And you'll see that all three fluctuate. And as you'd expect, the lateral bit and the vertical bit, they have a mean, an average wind speed of about 0, whereas your longitudinal has that very definite lateral. But that fluctuation is the turbulence in the wind, it's the gustiness. And that's what makes what we do very different from, anything like wind tunnel testing of cars, planes, or aerodynamics of more regular, much smaller bodies. Because when we're doing buildings, they're much bigger than the size of a lot of this turbulence or gustiness in the wind. So it's a function of that. All the pressures are a function of this gustiness, and we'll keep coming back to that. The first bit of everything we do in any wind loading study, looking at pressures, is to say, what do we know about the wind speed with return period or mean recurrence interval? Because that determines what you pick there is based on the standards in terms of the levels of reliability that you want to achieve. And so typically, if you're thinking a risk category 2 building, you're in there, right on your 700 years. Whereas this is just an example graph from a petrochemical facility we were doing, where they have to design for a 10,000 year mean recurrence interval. And we also have to look at any site at all the different types of storms. So what you'll see is the pink line there, and that's a statistical fit to historical data from usually an airport somewhere or some other meteorological station. So what we do is we go through however long, you're looking usually 10, 20, 30 years worth of data, and we go through and we sort out all the individual storms. and we rank them. And then we plot this, what we call a Gumbel fit to it. And that gives us a curve of wind speed versus mean recurrence interval. This one was not that far inland from the East Coast, so we had to consider hurricanes. Hurricanes are a thing that you don't have enough historical data on to be able to fit. So that's done through what we call a Monte Carlo simulation. And that's used throughout to come into the wind speeds and the hurricane course in the code as well. And then in this case, we also need to consider tornado effects. So we're looking at tornado intensities and how they rank in this site. And that's something, again, we're going to see in 722 is more of a consideration of tornadoes. So we'll look at that a little bit later on as well. Now that was just the all direction wind speed we looked at in the last graph, but we also need to consider how does the wind speed vary with direction. And this is the big difference between doing a wind tunnel study for building envelope pressures versus using the code. So the code is going to give you one wind speed that comes from all directions and then allow you to use a KD factor to get a little bit of a reduction. And we will talk about the KD factor because it's something that is not well understood by a lot of practitioners in the field, what it actually does. And we'll have a little example of that later on. So what you see here is we've calculated the wind speeds from all directions. We then scale that up, the green, so this is actually for Seattle, this one. So we got 98 mile an hour design wind speed for risk category 2. So we've scaled that up and we then put a lower bound on those wind speeds as well, so that there's no direction that we're giving undue attention for. And that's usually to get a sort of a pressure factor about 0.67, give or take. So this is just a comparison of ASCE 710 versus ASCE 716 wind speeds. And what you'll notice in Seattle, which I'm sure you have noticed by now, is that the wind speed, and this is risk category 2, so it's your 700 mean recurrence interval, they've come down significantly. And that's just due to more data being available, more reliable data being available. So what we've had in the States, as we've had in many other countries around the world, is mid-90s or so, the introduction of automatic weather stations, which meant we get much more reliable, more consistent data. We've also updated our statistical analysis techniques a bit, so that lets us trim things here and there. One thing you will notice on here that is particularly important up in the Pacific Northwest is you'll see a number of areas that are hatched out. And what they are is they're special wind regions. And that's usually somewhere where there's some kind of significant topography or unusual wind effect that can't be captured all that well by particularly local anemometers. So that's where you have to go in and consult either the local building code, or you get a specialist consultant to say, here are the appropriate design wind speed in these areas. You'll notice that there's a bit of a difference between 710 and 716 in the extent of some of these special wind regions. And this is a source of a little bit of controversy. So 716 goes back and it matches much better with some earlier versions of the code and the original introduction of the special wind regions. And then some of them apparently got a little bit shifted, a little bit extended due to printing errors at some stage. And that caused a bit of controversy within the code, but at the same time, it took some of the stuff that had been adjusted correctly, and went back to an earlier version, which wasn't quite as clever. And what we're going to see when we look at the 722 map a little later on is that that has been adjusted in a number of these areas and been corrected out for the next version. So just something to be aware of. The other bit that we talked about was, or we need to talk about, is the boundary layer. So this is again what makes it different from working in nice, smooth flow, uniform flow like you'd do with a more aerodynamic thing. The wind speed increases with height above the ground, or more correctly, it actually slows down the closer you get to the ground. And that's just from the surface roughness, the obstructions on the ground, creating a frictional effect and slowing the wind down. So if you're in an urban environment, very dense urban environment, so you slow it down more, you're going to see that effect on the wind speed for a greater height. It's going to be gustier. So that's really going from right to left as your sort of your exposure category D, going to your C, to your B, and then what used to be an A. And when we come to do our wind tunnel test, that's something that we need to be able to mimic or simulate. So if we look inside or on the outside of a typical modern boundary layer wind tunnel, you'll see it's pretty big. Here's our wind tunnel technician standing around. They're usually reasonably high, so let's just say they're about 5'10". Gives you an idea of the scale. So this section here, where you see boundary layer development through the working section, that's about 70 feet long. So it's quite a long thing. We get a good 100 feet total length of the tunnels. Fans around the back, and the flow circulates around. And that's what it looks like on the outside. So fairly substantial. If we look on the inside, here's what we've got to model that boundary layer. And there's some key bits here. So you'll see we've got some spires. We've got a little trip board, they're adjustable in height. There's roughness on the floor there, and that's adjustable. So we adjust that for every direction to correctly mimic the boundary layer that we expect from that direction based on the far field roughness that you've got upwind. Then once we get in closer to the building that we're testing, and this is just a little one in Austin, then what we've got is we've got all the surrounding buildings, usually within anywhere between 1,200 and 2,000 feet radius of the site that we'd expect to have a measurable specific influence on the building we're testing. The turntable there, that lets us rotate it, and it's usually tested at sort of 10-degree intervals. And we rotate it round and test all those directions to get a complete picture of the variation of the pressures with wind direction. So we can then pick the appropriate pressure, or calculate it, I should say, for the appropriate mean recurrence interval.
Roy, we had a question.
Yeah.
Are the number of spires variable?
Yes,
Right.
but no. So technically, yes, they are. You could do that, but we don't. We used to, in the old tunnel, we'd do that, but we're now set up so that they slide up and down and give different blockage. But if we wanted to go in for some reason and change the number, yes, we could do that, Nathan, yeah.
Okay.
Thanks for that, Chris. Now, the other thing you saw in there is this pitostatic tube. Well, you can't really see it. It's in the middle of that little green oval. And that's like the little pitostatic tube you see in the front of airplanes that sits out the nose and gives you a measurement of wind speed. And that gives us our reference pressure in the wind tunnel. And then we're measuring pressures at a tap, a little hole in the building model. And that pressure coefficient, that's the same as you see the CPs and the codes and standards. The pressure at that surface tap divided by the reference pressure gives us that pressure coefficient. And when we're working in the boundary layer wind tunnel, when we're working in that turbulent flow with sharp edged bodies, that pressure coefficient at full scale is the same as the model scale one that we measure. And that's the basis of absolutely everything we do. And it's what we call sort of Reynolds number dissimilarity. We can get away with it. So let's just look a little bit closer at one of these models. This is what you'd say is probably a fairly irregularly shaped building in the middle. It's a Frank Gehry special. It's the Grand project in Los Angeles, which we worked with a good structural engineer, DCI, Scott Erickson and his team on that project a few years ago. And if we look at the model, this one had somewhere, I think, in the range of 1,200 separate pressure taps distributed all over it. And if we look in zoom, you'll see here up near these sort of roof fins, you see the little hole there marked out in blue, and then you see that tube being drawn through the model, and then you see little bits of brass on the inside. And if we looked at the inside, that's what you're seeing. So you see all those little brass connectors going into the holes through to the outside. And then they all get connected up to this spaghetti of tubing that disappears through the floor of the wind tunnel to these banks of thousands of pressure transducers underneath. So whenever you do some of this wind tunnel testing, you spend a heck of a lot more time doing the setup and the calibration, the preparation, than the real testing.
Do you have a maximum number of those?
Yeah, so we've got two systems that run at 1,024 taps each at the moment. In theory, if we ever needed to, we could double them up and piggyback them to get 2,000 at once. But what usually constrains you is if you look at the inside of the model, there's only so many tubes you can get out through the bottom of the model at once. So it's usually a scale constraint that limits how many you come out at once. This picture here is a particularly large number because this was under the model on top of that. That picture was the Marina Bay Sands project in Singapore, which had this huge convention center roof. So we had a massive area underneath for bringing out those pressure tubes. So if we were to look at a sort of a time history, again, remember that time history we looked at of the wind speeds. This is two time histories of a building. There's square and plan. We've got the green is a pressure tap on the upwind face. The yellow is a pressure tap on the side face. So you'll see, again, pressure coefficient. And then on the upwind face, you'll see you got a positive pressure and it fluctuates. And that fluctuation looks pretty much like that gustiness in the wind. It's got that same regular, what we call Gaussian format about it. If we look on the side face, what you see is that negative pressure, which is sucking away from the building. And you'll see that occasionally you get these little peaks and they come whipping out. Yeah? And they're much larger than you get with the positive pressure. So that's what you recognize from your code coefficients that I'm sure you're familiar with. And one thing to remember is, where did all those code coefficients come from? They came from wind tunnel testing. So when we're doing the wind tunnel testing, we're saying, well, rather than a generalized set of coefficients that have been put in the code to try and envelope the majority of building cases, then we're getting something that's very building specific. So we're doing a couple of things. We're ensuring that the design reliability is met, but we're also able to say, well, we know that those code coefficients are conservative in a lot of areas, and we're able to show that they're conservative for individual buildings. So what causes those peak pressures? Well, the peak negative pressures, you see, this is just a little bit of smoke coming around the side of a building. You can see that little separation bubble underneath. You go, oh, that's not really very exciting. But then if you look over this one, which is just going over the roof eaves, you see that much clearer, and then you see the recirculation. So it's the wind pulling away from the surface before it reattaches. And that's what's causing that. That's a peak pressure. I should say this picture on the right was back when we were allowed to use nice smoke that gave really good pictures for this kind of thing. They've kind of banned us from using that now. Some health and safety nonsense that when it reacts with water, it turns to hydrochloric acid. So you did used to get the occasional stingy eyes and burning lungs if you'd been in there too long. But here's another example, and this is just a little movie. And let me just make sure I get the sound off on this. There we go. And this is another cause of the peak pressures. So, you know, you get that corner zone on roofs in the code. This is kind of the cause of it. It's what we call delta wing vortex. So you can see that sort of V shape coming out from the corner. And you think, well, that's kind of interesting and nice. You can do that in the wind tunnel. Does that ever happen in the field? And you go, well, actually, yes. And this is an example. This is actually 30 years old, this picture now. It was from the Burger King headquarters after Hurricane Andrew, I believe in '92. And you've got that perfect V scar. And when you're thinking about green roofs, landscape roofs, we kind of know that you're not meant to put gravel up there, but this is the same effect that we're seeing consistently scouring out some of the green roofs and preventing them performing in the way they've been designed. The other place we see this is we see a lot of roof mount solar arrays. And what we've got here is this is just a standard test model we used in the wind tunnel to try and develop some of the theory for this and some design guidelines that are now in ASCE 7, and they were in the COP PV2 before that. And you get that same effect. You get those little vortices forming over the corners. So you get the highest pressures. So the darker red is the higher pressures on this, with each of those sort of red pinky blocks being a group of solar panels. So you get the highest ones in the corner because the wind's coming from the top right there. And you'll see again, those leading edge, you get those much higher pressures. It's an interesting one in that we developed a lot of the science for doing this on the basis of failures that had been observed. And as sometimes happens with these things, we had manufacturers who initially didn't like the loads that we're coming up with and saying these are the recommended loads. After Superstorm Sandy came up the East Coast, probably was that 10, 12 years ago now, and you had a whole bunch of these balustade roof mount solar arrays ended up in sort of piles in the corners of the roof. That's when they started saying, all right, maybe you guys did get it right. And so a lot of this work has gone into the numbers that are currently in the standards for doing this. But what you'll see is the edge zones extend about 2 building heights in from the edge of the roof, and the loads typically go up when you add the parapets. So just important stuff to know. The other bit that is very important in everything we do, and this is just three graphs of pressure time history at different locations across a roof with time. And what we're showing here is that when the peak occurs in one, the bottom one there, the pressures are lower elsewhere. And that's why we get the area reductions in the code. So the bigger bit of building envelope you've got there that load shares, then the more the pressures come down. And it's just that area apart. The other bit to be really aware of is your approach to internal pressures. So you've got the external pressure caused by the wind, but if you've got any leakage or openings in your building envelope, then you develop an internal pressure. And that can work, for or against you, depending which side of the building you're looking at. But generally that gives you an increase. So what you'll see is these are the classifications that are in the code. So you've got enclosed buildings, which have a pressure coefficient of 0.18. And you say, yeah, that's because not much wind is getting in there to leak in. You're partially enclosed buildings, which says, well, actually we've got a fairly small hole or something getting closer to dominant opening. Then that pressure coefficient potentially goes up because more of that pressure can transfer to the inside of the building. Then a partially open building, you're saying, well, actually we've got so much leakage that most of that pressure is getting back out again. And open buildings, which are pretty much as you see, there's not enough building enclosure to generate that internal pressure. So this is a building you might recognize, being in Seattle. It's the Nexus building on Howell Street. And it's a nice little example of how we do a little bit of wind tunnel testing. So there we go. There's the building with its nice proximity model. We had, that would be 1,800 feet surrounding that, 1,600, 1,800 feet, somewhere in that model with the Seattle as was. But what I'm going to show you is we ran 2 tests on this one. So the building, you've got those sort of stacked, slightly rotated sections with some indents every so often. So the question came up, is that hurting or harming our wind loading? And the structural engineer, who's KPFF on this one, we're interested in that as well. So we said, all right, tell you what, let's run a more standard model as if you just had that uniform floor plate going straight up and down. So that's kind of what we've got there. And you see all the pressure taps there. And you get the typical output there. So on the left, that's just showing the mapping of the pressure taps. And this is the typical output that you get to design for. And it's showing, you know, the variation of pressures. In this case, it became reasonably straightforward in that you've got typically higher negative pressures near the top of the building where the wind speeds are higher. Reasonably sort of moderate pressures in the middle of the building. And then typically, once you get down a little bit lower, you'll often find the pressures increasing again. And that's because you get washed down the face of the building. And then this wind says, right, how do I now get around the building? So it's getting down near to the ground, it's being swept around, so you get this accelerated flow around the building. It's the same thing that gives you, you know, those gusts of wind or that accelerated wind as you walk about the city and go around the corner.
I think that actually answers an earlier question that I didn't get to.
Yeah.
But we've got another from Brett asking for apartments. What type of enclosure classification does CPP recommend, considering that windows may be left open?
Yeah, so that the enclosure classification is always a discussion with the end client or tenants, depending what you've got, in terms of what building management plans are, as well as the degree of operability of the facade. So, and that's very dependent on the wind climate as well. So for instance, if you're working down on the Hurricane Coast in South Florida, usually they've got, yeah, if you're talking a commercial building, they have very, you know, advanced sort of hurricane planning and building management procedures. So assume that's closed. You've got, you know, days and days of notice. So most apartment buildings there, you're going to assume they're going to be sealed in that event. If you're working somewhere where you have a more thunderstorm dominated wind climate, that's one where it's not as predictable. It's quite likely someone's gone out to the shop, left their windows open in their apartment, and you may have that. So it's always a discussion with the client. So if there's a reasonable possibility of parts of the building envelope being left open, then it can be wise to consider it being partially enclosed. But again, it's a discussion with the end clients and the whole design team to determine what's most appropriate.
Thank you.
Yeah. So this is just looking in at the nexus, as you know, and you'll see a few things. You'll see that we've got a much higher number of pressure taps because we always put this pressure tap density around building discontinuities. So what we found with the nexus was that the stacking of the cubes, the rotating, the breaking up of that edge, absolutely fantastic for the overall structural loads because it broke up some of the vortex shedding that otherwise you would have got, leading to some peak loads. So there was definite structural savings. But what you do find is that when you do this, you spin these little vortices up from these discontinuities. And so you do get little areas of increased pressures where you wouldn't necessarily expect them. And that's something, again, that's an area that the code doesn't cover very well. So this is one where I'd say, yeah, this is a non-standard building. Even it's not regular shaped, even though it looks in many ways to be fairly regular. When you see those little discontinuities, you go, yeah, that's something to be a little cautious of. Now, it wasn't like the pressures on this were crazy, yeah, but they were just, you were getting higher pressures in the areas where you wouldn't have predicted them just using the standard. But definite fun building to work on that one. So that's one where we looked at a potential change in building shape. This is another one where we looked at an actual change in building shape. So this is the UAE's pavilion at Expo 2020 in Dubai, where it's designed to look kind of like a falcon. So it's a Calatrava project. And these feathers coming around. So, I mean, falcon's the big thing in the UAE and the Arab states, a great prestigious thing. It's kind of their national emblem and animal. And these feathers lift up to reveal solar panels underneath. So in this case, because we've got two different forms, well, multiple different forms, but primarily they're just going to run them in fully open or fully closed. It was a building that had to be tested in two different formats. And that's definitely something you couldn't ever say was a regular shaped building. And again, what you'll see there is in the wind tunnel model, which looks remarkably like a photo I took when I went out there the other month to take a look at it as built. You'll see these pressure tubes running through the material. And so you'll see they're always almost in pairs. And that's to let us measure simultaneously the pressure on both sides to get that net load on those open wings. So that's one where you've got an obvious change in the aerodynamics between those two conditions. This is another interesting example of where the aerodynamics potentially change. And this comes back to what should you consider about for your internal pressures. This is the Las Vegas Raiders arena in Vegas. I don't know how many of you have seen it, but it has this huge opening, which actually on the other end, so you can get a view down of the strip from inside the arena. So massive doors that slide open and create this huge opening. So that's one where we worked with, again, with the whole team to say, right, here are the pressures and the load distributions with these closed. We also then tested with them open, so we had to measure pressures on the inside as well. Then worked with the team to come up with a management plan, because out there, again, it's thunderstorms are going to give you some of your highest wind loads, how to forecast them, how to come up with a plan for closing the doors if they're open when the weather service is saying there are thunderstorms in the region, then a backup plan if there was an electrical failure at the time to be able to manually close them, and then a full reliability analysis to show that even if they did get stuck open, here's the level of reliability that you have left. Here's our additional capacity. So fascinating project. But again, it goes back to that internal pressure question. Now, another bit that goes in there, rather than just it's door operability. And this is one that we're seeing more and more at the moment. This is just a lovely little video from a university campus, not too far from our lab in Colorado, where you get doors right on the corners. And remember, the corners are where you see those highest negative pressures. See, even the smokers have to come inside to light up when it's this windy in Colorado. But you see that? It's just pulled the side doors, it's overloaded them. The sliding doors are no longer working. And this became it was a real problem here. We had to come up with some screens for that, but we're seeing it very regularly. And this is just a relatively low-rise building. It's just very exposed. And those doors weren't correctly specified. Other fun things at the moment, paver systems, loose laid pavers systems. These are a couple that didn't work so well. And this is, again, a lot of these just rely on their self-weight. And you'll see these ones, they're pretty skinny, lightweight. You get the same uplift pressures on those. If the uplift pressure exceeds the weight, then they're going to take off. Once the first one goes, then you tend to get this cascading effect, because now the wind can get down into the cavity and just start peeling them back. This one on the left is an interesting one in that you see where the pavers have gone, and that pretty much follows the path of the accelerated flow from the downwash, because this is a tall building here with a little terrace, downwash, and round there, and was causing those to lift. The interesting solution to this one was actually to stick a sort of a solid gate in here to just break up that flow across there. The problem was my understanding of solid and the architect's understanding of solid on this one was a little bit different. So they interpreted solid as heavy, so put in a lovely, beautiful wrought iron gate in there, which it was solid, I'll give it that, but it was also very porous. So it wasn't really stopping the wind at all. So we had to have another little conversation about that one. Now, here's another thing to be a little bit careful of. This is a set of perforated panels, and we're seeing more and more issues with sort of perforated panels, whether they're on parking garages or screening rooftop equipment and making wind noise. So what you see here is a section set up in the tunnel. We've got a microphone there, and this was a sample that was sent over from site after it had been installed on the site and started whistling, so that we could then work out some easily applicable sort of mitigation measures to stop that. And wind noise, it happens at all kinds of scales. So we've been working on this kind of perforated material that likes to whistle, and in this case, it was actually the gaps between the panels which weren't lapped together that caused the primary noise. We've seen just straight plates with their own perforation pattern. So if you're specifying that or see it specified in a project, ask the supplier if they've done testing, and they'll guarantee that it's not going to make noise. Because once you get them on site, and I know of at least one here in Seattle, not a million miles from where I'm sitting right now, that wails like a banshee on a particularly windy day. And that too is an interesting one, in that the building owner, obviously not very happy, went back to their design team and said, got to fix it. The design team looked at it and decided what they thought the cause of the noise was and applied a fix without actually testing that that's what the cause was, and it didn't really help. So we got brought in later to do a proper investigation, work out what the source of the noise was, and come up with some mitigations. So here's some other perforated components, and this is just another little cautionary tale. This is a sort of kinetic sunshade, and each of these panels is able to rotate and swing. But what you got here, because you got a dynamic structure, is you got feedback between the plates and that central mast. So this video on the left was taken just a few hours after these panels had been installed. And you can see that swinging fairly significantly backwards and forwards. And this again is at the Expo 2020 site in Dubai, where there's, I think, 50, 55 of these going up. And this was the first one to get the panels on. So you get out there, and with a bit of rope, you can really get these things moving. It's kind of fun. So just watch when you've got sort of kinetic elements on the building envelope, think about, or the structure, how the feedback is going to come back. So that's some of the final ones. Once these all got tied together, that problem ceased to exist. So just some cable netting went across, some additional stuff, and that settled everything down. Now, what we're also looking at through here, we're seeing some sunshades, and this is on the Mobility or Opportunity Pavilion. I forget which one it was. It was a Foster's designed one. So this is what these look like from the outside, and it was determined that these had a potential to vibrate significantly in the wind. I think it was possibly slightly overstated, yeah, but as a result, each of these has got, I think, you average about 6 little tune mass dampers inside, just to mitigate it. So it's a component of the building enclosure, the building envelope, but it has a significant dynamic structural response, or potential dynamic structural response. So we see that in much smaller scales as well sometimes. So we've seen sunshades and louvered sunshades in buildings where the individual louvers start vibrating at quite high frequency and can fatigue and fail, or they make such a hideous noise that they need a little bit of treatment to calm them down. So one of the questions I get asked on a very regular basis is when to wind tunnel test. And my answer is always as soon as it's practical to do so. So in terms of the building enclosure, the building envelope, you know, for normal building and structures, as soon as you've got that form, you don't need to know the materials you're going to build it from, or you're going to use initially, yeah? But you do need to know what shape it's going to be. One of the things that we find in wind engineering is that there tends to be a little bit of an assumption that we go in and do the wind tunnel testing, and it's a bit like doing a component test. You do it, you prove it, there's the numbers, and you do no more. It shouldn't be that way. You get much more out of a wind tunnel if you use the engineers who've done it to actually do some consulting as the project develops. So as you're looking and saying, well, actually, we want to change from this type of system here, we're going to move it slightly this way, you know, we're going to move that 12 feet, and maybe that wanders into one of the other pressure design zones that are on the elevations we're looking at before. If you get that, then, well, go back to your wind tunnel consultant and say, hey, look, how fixed is that line? Because we're making assumptions, yeah, and it may be, you know, a few feet here or there. Yeah, we've got a bit of conservatism. We can make that a little bit better, you know? For unusual or wind-sensitive structures, use the wind tunnel early to provide proof of concept. So a nice example of that was that UAE Expo Pavilion. We tested that very early before we knew about many of the surroundings at all. Just to show, right, here are the pressures on this. That's our starting point. So it gave that proof of concept. Between then, over the next sort of 18 months or so, they developed a lot of the rest of the buildings surrounding it, including the central Al-Wasl Plaza here, so you have a huge dome. So we then had to go back in and retest to take account of that. Another time to wind tunnel test is if you don't believe the results you got from your first round of wind tunnel testing. If you don't believe it, and I mean, I've worked in, you know, multidisciplinary consultancies where I've been reviewing wind tunnel tests. Occasionally you'll get some from somewhere that you just don't understand. And if your wind tunnel consultant can't explain it, get it peer reviewed. Or if it's really costing you, you know the cost of a building envelope relative to the total construction cost and relative to the cost of doing some wind tunnel testing, it's huge. So it can often be worth doing that second round of wind tunnel testing. What I would say is the experience shows that people who are using the appropriate techniques, the pressure coefficients are usually pretty consistent. The big differences usually come with the interpretation of wind climate. And then the other one is when you realize that you should have done it before construction. And we're seeing more and more of that with typical door operability is the biggest place we see that in terms of the building envelope. So what are some sort of reference sources if you want to read more about the wind tunnel testing? Well, we've got a standard that says there's our minimum standards for wind tunnel testing for building and other structures. That's something when you're sending out a request for proposal for a wind tunnel test, refer to that, say, make sure you're following this. There's Manual of Practice 67 from the SEI. It's got a lot of background information. It's out of print now, but it's only slightly dated. It's pretty in-depth. For the taller buildings, you get the SEI Manual of Practice 143 that was just published last year on design and performance of tall buildings for wind. And that gives a really nice overview of all the bits that go into that, largely from a structural point, but there's a bit of building envelope in there. And then there's a guide by the Council on Tall Building to Urban Habitat that's, again, it's tall building specific, but it's written in plain English, or since I wrote large parts of it, I'd say plain Scottish maybe.
I did have one question. Yeah. The question from Jeff reads, how are design solutions to build conditions determined? Are they modeled, site testing, mock-up, something else? I think he's talking about sort of solving problems in the field or testing solutions.
Yeah, so if you're running up against a problem in the field, you've got to try and work out what the cause is. And it's really horses for courses. Sometimes we think, well, actually, maybe there is some huge pressure that the code wouldn't have predicted. So you go in, you test, and you say, actually, yeah, that did get under specified. Here's what it needs to be specified for. Other times, if it's like the noise stuff, I mean, we do plenty of just taking the prototype samples and testing those. There's another one, there was a project in Las Vegas that was making some really unpleasant wind noises. And it was due to sort of a cavity resonance that you wouldn't have expected between sunshades. And that was one where we spent probably 3 to 4 months convincing ourselves of that was the cause of the problem. Because it wasn't something that could be modeled, because it only appeared at full scale in the field. But we were out, we had arrays of microphones across this roof deck between these two towers. So we were working out phase shifts and then sort of doing computational modeling of the pressure waves to see if it was repeatable. It's always good fun doing that stuff, but it's challenging. There was one that we did in the UK, which is the Beetham Tower in Manchester. So it's the highest building in Manchester at the time. I think it probably still is. And it had a series of parallel vertical fins on the roof, and still does. And this set up a sort of a phase locked, pressure wave behind it, which was creating huge noise, such that the TV studios a couple of miles away, where they filmed the most popular soap opera in Britain, had to stop filming on windy days because of the background noise from the building. Interesting one, because the architect had the penthouse, so he was particularly interested in solving it. But they had a whole bunch of people came in and said, we think it's this, we think it's that, and they tried solutions. They weren't working particularly effectively because no one had actually spent the time to really sort of test their theories and confirm that that's what it was before going for a fix. So yeah, don't always jump into assumed fixes, I guess, is the message from that.
Are you doing any sound testing at the wind tunnel level at those small scales?
Not at the small scales. We're actually using prototype components. So if you saw that slide a few back, where is it? That one there.
The panel, yeah.
So that's actual prototype. I mean, that's samples delivered from site that we're mounting on a frame. And you'll see in this case, because you think, well, the wind comes flat, but the wind isn't always coming flat relative to vertical surface because it's kicking up and over a roof, so it's hitting it at an angle. So we test these things at a wide range of wind angles, both relative to the horizontal and the vertical planes. So it gets a bit in depth sometimes. On occasion, we've actually had to go out and, because the stuff is too big to get in the wind tunnel, actually build a mock-up, on a building out in the field. And we've kind of been lucky in that we did some testing for the Roof Shingle Manufacturers Association, probably about 20 years ago. And they paid to build, a little part-size house on a turntable up on the Wyoming border, where the wind blows in every afternoon from the same direction. And the power station said, yeah, I could come and use our site. And we stuck up a meteorological mast for wind speeds, and we were actually able to use that for a lot of sort of field verification of this type of stuff.
Do you test components like those sliding doors that we saw, or pieces like that?
We don't. No, we generally stay at the sort of component testing in terms of the performance bit. It's more just noise stuff like that.
Okay.
We have gone and done some full scale set field testing on things like solar arrays, and that's just to say, well, look, come on, we potentially have some scaling issues when we get into the wind tunnel because of the gaps and the number of tubes. We need to make sure and use this as verification that our wind tunnel techniques, which we think are good, are actually doing and can be replicated in the field. So that's kind of the level that we do the bigger scale stuff at.
Okay.
Let's zoom back down to where we are. The other one that's you may come across at the moment is the Prestandard for Performance-Based Wind Design. That was 2019, I think we published that. And a lot of that is to do with structural design and allowing some degree of plastic behavior in the structure while showing that reliability goals are still being met. But there's a very large chapter in that on the building envelope. And so if you're going to do performance-based wind design for the structure, that's all well and good, but you're not protecting the contents of the building unless you have an equal reliability in the building envelope. So if you're going to do performance-based design for the structure, you have to also do it for the building envelope. If you want to do building performance-based design for the building envelope, it permits you to do that without doing the structure. So it kind of works both ways, but it's definitely worth a read. And you can download that from ASCE for free. It's not one you need to pay for, which is good news. But we'll get on to a little bit of reliability in that coming up. So let's just have a quick chat about major changes that are going to affect sort of building envelopes and enclosures from ASCE 716 to 722. Wind speed maps. There's 716 on the left versus 722 on the right. And what you'll see is nothing much has changed up here in the Pacific Northwest. The numbers are the same, so no change there. Where you will see is going a little bit further west in some of these special wind regions that we talked about. This is the Front Range where I live. And this is one that got incorrectly moved back in 716 from what it should have been, and which has now been reincorporated into 722. So generally the 722 maps are a bit more reliable. The one place that outside special wind regions that we do see a change in 722, a significant change, is down around the hurricane coast. So your extreme areas like southern Florida, no change. You'll see around here, around the Panhandle, there's a bit of a change in that the wind speed contours are getting closer to the coast. And that was a finding from Hurricane Michael, which tracked in much faster than the models would have anticipated. And it was almost impossible to replicate that with the current models. So that went back to the hurricane modelers, and as a result, they modified their models and changed them until it could replicate that. So that's one of those bits that where we're starting to think, yeah, we do really have to plan for some of the global warming and climate change. This is possibly one of the bits of it. And there is a panel being set up at the moment to look into what we ought to be doing as an industry in terms of anticipating climate change, accounting for it in some of these wind speeds, which are, for the most part, anywhere inland away from the hurricane coast and on the west coast, derived purely from historical data. The other bit that we've got in 722, it's still got those wind speed maps we looked at, but what you'll see is the hazard tool from ASCE 7 that is now completely open, full access at no cost. So that becomes the reference rather than just the maps in the code, which is good. There were a couple of issues with previous versions of the hazard tool. So if you remember, you had the SC hazard tool, and there was also one that was done by the ATC, the Applied Technology Council, and sometimes those gave slightly different numbers. We now know why, and that's been resolved. They're in line, and so the ASCE version is very much the standard. And it'll also give you a nice sort of PDF printout if you're into that kind of thing to chuck into your design documentation. One thing you will notice is that the design tables have been deleted. So they were kind of the shortcut so that you weren't doing all the calculations. But it was pretty much a decision of the committee that design tables like that belonged in design guides rather than the standard itself. And I think relatively few people were using them because most people have got something coded up themselves to do the code calculations for them. So that's one thing that's made it a little bit thinner. We also have pressure coefficients now for canopies and taller buildings. In previous versions, it only got you up to buildings from 60 feet, we now have that for buildings over 60 feet. And that's been something that's been missing for a while. So that's a great addition that I think you're going to find really useful. We also have something on roof pavers. And we looked at some roof paver failures before. What we didn't talk about is the fact that if you designed your roof paver to resist your pure roof uplift pressures, you would be conservative for elevated pavers. And the reason for that is that you've got little gaps between the pavers, and that allows some degree of pressure equalization, which reduces the effective pressure on them. So we've now got an allowance to do that, come up with a net uplift pressure coefficient. So basically says you use your roof coefficient, or you determine the coefficients from wind tunnel test performance in accordance with chapter 31, which is the one that says, here's how you do your wind tunnel testing. And that now aligns much better with the ASCE 49 standard for wind tunnel testing, or determined by methods described in the recognized literature, which is a normal way of doing it, which all the rest of the thing through the code says you can use code values, you can use wind tunnel as an alternative route to compliance, or you can use methods described in the recognized literature. So that's basically most stuff that's been in some kind of peer-reviewed publication. So what that does is that lets us introduce a reduction factor to get into there. You also see the KD factor, and I told you this is when I was going to come back to it. So that's your directionality factor. So you'll be quite used to that. And you apply 0.85 to all the pressures you calculate from the code in a regular building. So what's that meant to do? The idea there of the KD factor is to say, well, chances are my peak pressure coefficient on a building, I mean, the pressure coefficient varies with wind direction. Chances are that's not going to coincide with the statistically strongest wind direction. Sometimes that's true, sometimes it's not. And it's an average value. So it means that just about every building, you're going to have something that you use 0.85 with, it's going to be unconservative. The other part of that a lot of people don't know is that KD factor is for individual elements of the building enclosure or the building envelope. It's not for the building envelope as a whole. So when you integrate, if you use your 0.85, on every individual bit, somewhere statistically on your building, you're going to have something that would not resist the design level wind. So if you want a completely reliable building envelope as a whole, you really ought to be using a KD of 1. We tried to get some stuff about that brought into the code, got a huge amount of kickback, but it's not a new idea. And it's actually in a FEMA publication from about 10, 15 years ago, I think now, where they're looking at sort of mission critical facilities and saying, for these, the ones with post-disaster functionality, you ought to be using a KD of 1. And somewhere that's worth discussing with your clients is the clients who have that post-disaster occupancy requirement. And that can be things like hospitals, but it's also things that have, very high value contents, or where a period of inoperability of the facility would come at huge cost. And one where we see that a lot right now is things like data centers. So just one to bear in mind.
Or can you talk about the difference between LRFD strength design pressures versus allowable strength design pressures?
Sure. So this is where it gets a little bit interesting. So let's just go back to the wind speed maps. So this is what your wind speed maps look like now. So these are wind speeds for the risk category that you're interested in. So these are risk category 2. So you get 700 years. For risk category 3, it'd be 1700 year wind speeds. Risk category would be 3000 year. Now, if you go back to ASCE 705, what you had were wind speed maps for use with ASD design procedures. So what that did was you calculated the pressure with that, and then you multiplied by 1.6 to get to the ultimate, if you like, pressure. What that meant was that in terms of this wind speed map, these contours in ASCE 705 and earlier versions, everyone thought they were 50-year contours. That they weren't. They were nominal contours where inland, yeah, it was about 50 years, but you came out to the coast and it was rather higher than that because the rate of change of wind speed with the return period, it's a much steeper curve in hurricane regions. So they were never 50-year wind speed maps. They were wind speed maps that once you calculate your pressure and use 1.6 on them would get you up to this 720-year wind event or wind loading event. Where we are now is that you've got these ultimate ones, which say you calculate your pressures, yeah, and that's what you would want to ensure that your building envelope could withstand, to ensure integrity there and no leakage or failure. What you find though is that most building components are still rated based on an ASD pressure. So you then have to take those numbers, and if you believe the code, yeah, you'd say multiply by 0.6, it says, where in fact it should really say multiply by 0.625 because it'd be the inverse of 1.6. Something that causes all kinds of fights on the code committee. So there's a little bit of understanding of how your components are going to work. What you'll see, and this is where it's actually worth reading the chapter 8 in that pre-standard, because it talks about performance goals for different risk categories and performance goals for the building envelope under each of those. For limited interruption, or continuous occupancy, it's classified in that way. So it's kind of following a bit of the seismic work and bringing it into the wind environment. So that, I don't know if that quite explains it. It's a massively complicated subject. I could speak for about 3 hours on and give you 15 different answers, because 15 different people involved in this all have slightly different takes on it. But generally, yeah, you're looking at, for a risk category 2 ASD, it's roughly a 50-year mean recurrence interval versus a 700-year. And it's the 1.6 load factor that makes the difference. Yeah. Right, here's the other new bit in the code, is that there's now a chapter on tornado loads, and it is separate from wind loads. We're not considering this a wind event within the code, it's a tornado event. Where this is, there's a nice little map that shows you tornado prone regions. So if you're working over here in the west coast, forget about it. If you come over here and basically anywhere east of the Rockies, you've got to give it consideration, but only for risk category 3 and risk category 4 structures. And for a lot of this, it's going to be a quick check to show that it doesn't govern. But for some of the more critical and larger buildings, then it will come into play. So here you go. You've got wind speed map or tornado speed maps for various risk categories, as you've got for the wind, but they're also provided separately for different areas. And the idea is that as the area of your project goes up, the more chance it's going to be hit by a tornado. Pretty simple, yeah? And that kind of makes sense. It uses a lot of the same techniques as you'll see from the wind chapters, and in fact pulls some of the coefficients direct from the wind chapter. So you get GCP there, that's coming straight out. But we've got a different internal pressure coefficient because you're more likely to have some penetration in the building envelope from flying debris. You've got a different directionality factor. And then you've got a pressure coefficient adjustment factor. And that's to recognize that the pressure coefficients that we use through the rest of the standard have been developed from wind tunnel testing and classic boundary layer profiles, where there's no real vertical component to the flow, or to the mean flow at least, where we do have that within a tornado. So that they did a whole bunch of tests on buildings canted at different angles relative to tests and came up with a bit of a fudge factor is what it really is. But it's kind of as good as we get. And it's what I would say is the tornado chapter. There has been a fantastic amount of work put into it by a lot of really clever people, and it's a massive advance forward. Having said that, it's early days. Is it as fully developed as something would normally be before getting into a standard? I think it's fair to say that it's not. No? But is it correct to have it in the standard at this stage? Absolutely. When we look at the losses that are incurred each year from tornadoes, relative winds, and the risk to life, it's absolutely right to be putting this in early. But it's one that you would expect to see develop fairly significantly over future versions of the code. And that's about it. I've probably exhausted everyone.
No, I think that
Trying
was
to
great.
go through too many things in about an hour. Yeah.
Yeah. No, great job. I got a couple more questions in the queue here, and if anybody else wants to add to the Q&A, please do. One from early on asks about if the holes in the models weaken the model. And it looked to me like those are sort of 3D printed.
Yeah. So all those models where we're measuring the pressures, you'll see they're SLA printed, so they're out of laser hardening resin. And that is airtight, which is why we use that, whereas some of the other 3D printing methods are not. But if you put in too many of them, yeah, you would weaken the model, but you change the aerodynamics a little bit as well.
Sure.
But no, there's no significant weakening to the model.
And then in your wind tunnel, so after the air comes rushing down the corridor behind you there, where does it recirculate back into the other end? Yeah,
so there's a lot of different kinds of wind tunnels. All the ones that we run are recirculating wind tunnels. So it goes back around, and the fan is actually, rather than pushing it, the fan is actually pulling the air past you.
Oh,
so is
that less turbulent?
No, it's just more efficient.
Oh.
Yeah. But no, it's kind of fun, and we love it when people come and visit the wind tunnel, and you actually take them in there and they see the scale of that in person. They kind of go, wow.
Yeah. Let's see. Can you just touch again on the type of buildings which you should consider for wind tunnel testing? I know we talked about odd, irregular shaped buildings, but is there a height limit or any other kind of?
Yeah. You know, it's anything that kind of falls outside the scope of the code, and there's no black and white answer. So there's plenty I can look at and say, yeah, just use the code. It's not going to make a difference. Where I'd say it becomes more important is what's the cost of the building, or the value of the building, or the value of its contents. That's probably what drives it more. And we've done everything from single family houses, all right, it may be high net worth families with pretty extreme architecture in their housing, but again, they want that level of reliability. And I think everyone recognizes the code doesn't always capture everything. And my expectation is, I mean, we've talked about sustainability for years. I mean, the buzzword now is resiliency. So there's the US Resiliency Council. I've got a seismic resiliency guide. We're in the early stages of preparing a wind resiliency guide. And I'm kind of expecting that to start feeding into, you know, the insurers, the reinsurers, how they assess the building and the insurance costs associated with it. And there will going to be points for stuff where you can show that a good wind tunnel test has been conducted. So I think we'll see more and more of that. I mean, people tend to think it's the high-rise buildings, but we do a ton of data centers just because there's a reliability requirement there from the ownership. And they want to make sure they've got sort of belt and braces on that stuff.
Let's see. And then Dave Young asked, if the paver pressure coefficient is the same as the ANSI Spry SRP4?
I'm trying to remember what the answer is. All right, yes, SRP4 is. Do you remember which one that is, Nathan?
I don't know. No.
All right, so
Ballast uplift.
Okay. No, it is different from that. Thank you, David. Yeah, it is a bit different. So the coefficients, we've done some work, yeah, and we've tested, and I thought I'd left a couple of slides, and I probably took them out for time, of some full scale testing that we did in the wind tunnel to look at the effects of the gaps between the pavers and the space underneath them, and the effects on the net pressure coefficient. But if you're looking for a sort of a rule of thumb on that, you'd say you're probably, a safe number would be sort of assume roughly a 30% reduction compared with just the straight uplift on the roof as a general rule. I mean, it depends where you are on the roofs, all that kind of stuff, but it's a starting point if you're looking at that kind of thing.
Okay, well, I think we've exhausted our bank of questions. We really appreciate your time today.
That's been a pleasure. Thanks for the invite.
Yeah, all right. Yeah, glad you got out to Seattle, even though we didn't get to meet you in person yet.
Yep. Yeah, and if anyone has any questions, just look up the CPP website and you'll get my contact details there. I'm always happy to answer questions.
Great. Well, we look forward to seeing folks next month when we talk about architectural concrete with Brad Carmichael from 4EA. And until then, everybody take care, and we'll talk to you again soon. Have a great afternoon.
Thank you.